and mark a point 2, 3 down in the domain. Mark a point 2, 3 down in the domain. How many people are following? How many people? If I can see your lovely faces and they make sure, I'm going to call on people that don't have their cameras on. Yeah. Okay. Now focus. Don't draw anything till I tell you. We're going to draw a unit vector. We're going to pretend. We're going to draw a unit vector down in the domain, sticking out from 2, 3. Its butt will be at 2, 3. Draw a unit vector, mark it as u, and you can pretend how long 1 is. Draw a unit vector, mark it as u, heading out of 2, 3 down in the domain, the xy plane. Okay, now draw another vector, but at 2, 3. Mark it as w, it's another unit vector, make it a different direction than the vector you picked. Make it a different direction than the vector you picked. And then I'm going to catch up over here on this board. What's the first thing I ask you to do?
Draw an XYZ.
So I'm going to do the same thing. Then what did I ask you to do?
Draw a space sheet.
Space sheet, so we got this. Space sheet, what do we label our space sheet? What do we call it?
Z equals f of x, y.
Z equals f of x, y. Then what I ask you to do? 2, 3. And so now I'm there. Then what did I ask you to do?
Draw a unit vector u.
So I'm going to draw a unit vector, and I'm just going to pick mine going like in that direction. And then what did I tell you to do?
Draw a unit vector w.
Draw a unit vector w going in the other direction. Okay, the next thing I want you to do is I want you to go straight up. So we're imagining we're kind of in the domain. We're standing right at the point 2, 3, and we're looking up under our space sheet. And I want you to mark the point on the space sheet that would be directly under the point 2, 3, and give the coordinates, give the 3 coordinates of that point if you're going to explain to somebody how to get there with a ladder. They're going to start at the origin and have to get there with the ladder. Okay, what's the z coordinate of that point? What's the z coordinate of that point?
F of 2, 3.
F of 2, 3. We just plug it into our function. We plug x is 2 and y is 3 in, and we get f of 2, 3. And then what are the coordinates of the point actually on the space sheet? What is that? You go down the x-axis,
2.
you go over on the y-axis,
3.
and then you go up,
F of 2,
f of 2, 3. So that would be my 3 points. How many people are following? How many people are following? Okay, now I want you to draw a line, a domain curve. Draw a line, it's going to be a line, that has a direction vector of u down in the domain. Draw a line through the point 2, 3 that has a direction vector of u down in the xy plane. Now, when I say line, you say, I hate you, Dr. One. When I say line, you say A plus TD. Okay, so if I'm looking at that line, what works wonderfully for a direction vector? What works wonderfully for the direction vector?
u.
U, the vector u. So let's over here, let's just write down here. My D here, this is direction vector, has nothing to do with derivative. My direction vector is really going to be u, and right now it's arbitrary. So let's just call it u1, u2. And the only thing I know about this is it's a unit vector, so its norm would be equal to what? Its norm would be equal to what, guys?
1.
1. So let's just remind ourselves of that. Not that it's real important in this argument, but it will be in other arguments. Okay, now I need a position vector. You hopefully drew a line that, my line might look something like this. My line might look something like this. I need a position vector from the origin that would point to the line. Can anybody think of what might be a decent line?
2, 3.
2, 3. So let's just, that would be like my A. That would be my A. And when I say line, you say,
A plus TD.
A plus TD. So I'll just write that down. A plus TD is going to be my line. But my position vector is just 2, 3 plus T times my direction vector, which is just
U1, U2.
U1, U2. Now, how many people can do vector addition? How many people are pretty comfortable with vector addition and scalar multiplication? So then write this as a two-dimensional vector value function. Write this as a two-dimensional vector value function that will mark as R1 of T. Write that line as a vector valued function, which means I need functions in the X and the Y. So this line down here is R1 of T. This line down here is R1 of T. Okay, what do you guys have for the first component? What do you have the first component? 2 plus TU1. So let's write that down. 2 plus, and I guess I'll put, since it's just a constant, I'll put the U1 first. T. 2 plus the constant U1 T. And then how about as the second component? The second component.
3 plus U2T.
Okay, now this is going to be a little bit difficult. The most difficult thing is for you to focus. So stand up. So it's not, that's the most difficult thing. Just stand up. Robert was up immediately. No, Robert's not standing at all yet. Robert, there we go. We're up. Almost up. Oh, okay, good. Nick, you better be standing. Nick, you better be standing. Ava, you better be up. Stretch. Yeah, stretch, because you're gonna need this. This argument took the entire hour and 15 minutes. So sit back down. It's really, really important. I thought it would take 30 minutes, but I never thought it would take an hour and 15 minutes. So I told you about Doug, what Doug did with Sam. Did I tell you about that? The death march. Did I tell you about that? Yeah, so this is what you're going to feel like. You're going to feel like Dr. Morton's being Doug today, taking you on the death march. Okay. So I've got this line running through the point 2, 3. It's 2 plus U1t and 3 plus U2t. It would be a domain curve if there was some value of t that I could plug in that would actually hit the point 2, 3. It would be a domain curve if I could actually find a value of t that I could plug in to hit 2, 3. Can anybody see the value of t? What's the obvious value of t that you would plug in that you would get the point 2, 3? 0. If I look at that, my c value, R1 of 0, is the point 2, 3. Now imagine, Dr. Warren, stop. Now imagine that I plotted every point on this domain line. The line running in the u direction. Imagine that I plotted every point running on this line up here on my space sheet. What if I looked at every point in the domain on that line and plotted it with its z coordinate on that space sheet? Would it run through this point? Would that have to run through that point? In fact, it would look like a what, guys, if I actually drew it? It would look like a what?
A line.
It wouldn't necessarily have to be a line, but you're thinking in the right direction. It would be
Space curve.
a space curve. It's definitely a line down here, but depending on how my sheet is folded above my head, do you see that it won't necessarily be a line above your head? It's going to be like a space curve. When I say space curve, you say R of t, a vector value function with three functions. Okay, so let's try to draw this. Now, we really don't know. I'm imagining it on here, and guys, I don't really know because it's right now just a sheet, but I'm imagining that maybe when I'm coming here, I'm going down, swinging into here, and who knows, maybe there's some topography with my space sheet, and then I'm coming up over the hill like that. So I'm imagining that this is the direction of my line, pointing in the u direction, and this is creating a space curve. This is creating a space curve up there on my space sheet. Can you guys visualize this? Can you guys visualize it? Okay, now I don't want to use R. Does it make sense why I don't want to use R? You're like, well, Dr. Warren, you've already got an R. So I need another letter. I need another letter that's going to represent a vector value function. And you're not going to like it. I'm going to use S. But guys, so far S has always been exclusively, I forgot already, Dr. Warren. S has always been associated with arc length. Okay, so we're going to use a vector S. I'm going to use an S1. You're like, oh crap. If there's a 1, there's probably a 2. My S1 of t. It's going to be this space curve. It's going to be the space curve up on the space sheet. Well, it's got it. Oh. What do you think? You think I can do a hook shot into that trash can there? You guys think? What do you think?
Yeah.
Hook shot. Oh! Block. LeBron. I don't know why I love that song, LeBron got dunked on. James got dunked on, sorry. I know nothing. Don't listen to me. I always think of LeBron, and James got dunked. I used to play music in my classroom. But since I'm recording it, every time I do that, I get a copyright violation from YouTube. And they won't post the video. Even if I just play like James got dunked on for like 5 seconds, I get a copyright violation. I'm like, holy hell, I'm using it to teach math, to wake my kids up. And you're gonna flag me with a copyright violation? Did you not look at the video and realize it's Calc 3? Okay, but back to where we were here. A vector value function is called a vector valued function because there's 3 functions in the vector. What would be the first, if you're plotting all the points on this curve, which is following this line in the domain, what would be the first component in that S1 of t? Write down what you think. Write down what you think. If you had an eraser, that might help. What do you think the first component in that function would be? And then, if you're lucky, go for the second one. Go for the second one. You're using all the points. You're using all the points on that line R1 of t. You're plugging them into the function and plotting them up there on that space sheet. So what do you guys think? What would be the first component? What do you guys think the first component would be?
2 plus U1T.
2 plus 2 U1T. The first component in my line. 2 plus U1T. What do you think the second component would be? What do you think the second component would be?
3 plus U2T.
3 plus U2T. How many people are following? Are you guys following at home? Are you guys following? Are you following where you're at? Okay, how about the third component? You're like, well, Dr. Warren, that's the one that's going to send me up to the space sheet. That's the elevator that's going to send me up to the space sheet. So how would I get that third component?
The f of xy.
Yeah, you plug in the f of xy, but the x coordinate is 2 plus u1t. The y coordinate is
3 plus U2T.
so it would be f of. I'm writing pretty big. It'd be f of 2
plus U1T.
comma
3 plus U2T.
3 plus u2t. Now you're really gonna hate me. do your very best to draw the tangent vector to the space curve S1 of t at the point 2, 3, f of 2, 3. Do your very best to draw the tangent vector to the curve at the point 2, 3, f of 2, 3, up there on that space sheet. Whichever, you guys might have drawn your own curve up there. I drew mine kind of going down. And I'm running in this direction on mine. I'm running in this direction. So I've got to ask, would that be the tangent vector? Now look, here's the point. Does that look like that's tangent to the curve? Does that look like that's tangent? And your answer better be hell no. Okay. If I'm thinking about it, might be something like that. Does that kind of make sense? This would be like the tangent vector to the curve. How many people feel like they understand that? How many people feel? How do you get tangent vectors to curve? Oh crap. How do you get tangent vectors to space curves? How am I not giving you guys a cumulative final? How am I not? How do you get tangent vectors to space curves? R prime of t. But now I don't have an R, I've got a S1 of t. So you guys are going to help me out. Let's start. We're looking for that tangent vector. So you guys are helping me out. I've got S1 of t. You said take the derivative. Okay, remember U1's a constant. How many people are pretty comfortable with? How many people are like, Dr. Warren, I think I've got the first component. What would the derivative of the first vector value function be? What's the derivative of 2?
0.
What's the derivative of 5t? Dr. Warren, there ain't a damn 5. What's the derivative of 5t? 5, 7t?
7.
A constant U1 times t? U1. Like, Dr. Warren, we're flying. How about the derivative of the next one? How about the derivative of the next vector value function? U2. A wonderful band, I'll let you know. A wonderful band from my generation. Okay, U2. Okay, now, how about the third one? And you're like, oh crap, holy hell. It's a function that's pregnant with two other functions. It's got twins. It's got two components. This is a function of t, and this is a function of t. Damn it, if we only had a chain rule. Oh, guess what? We do have a chain rule. Now let's see what you remember from your chain rule. Do not look at your notes. Roberto, you better not be looking at your notes. I'm looking at you there. You better not be looking. Michael, you should look at your notes immediately. Oh, you don't. You only have a sheet of paper. Okay, I've got a function f of xy. And let's just pretend the first component is a function of t also. And the second component is a function of t also. So we have a function that's pregnant with twins. And I'm wondering, what's the derivative with respect to t? What's the derivative with respect to t of that function theoretically? What does it equal? Write down what's in your gray matter. Write something down. Do not write nothing down. Whatever you got, it will probably be wrong, but it's okay. You can be wrong. Write whatever you've got in your gray matter. I can't be wrong, Dr. Warren. No, you can be wrong. You can be wrong. It's called learning. Okay, show me what you got on the grid, guys. Hold up something. Whatever you got, I want to see what you've got. Emily, what do you got for me? Cameron, what do you got? Zachary? Hunter, I'm liking a lot of that. There's good stuff there, Hunter, but it's not quite right. Rachel, I like a lot of what you got there, but it's not quite. Robert, you're a little blurry, Robert. You're like Dr. Martin, you're a little blurry too. Okay. Okay, let's see. Does anybody have, how many people remember this? There's a plus. How many of you remember there's a plus in the derivative of the chain rule? You're like, ah, crap. I totally got it wrong. What's the first part, first term? The partial derivative of f with respect to x, evaluated at x of t, y of t. Are we done? No, it's chain rule times what? The chain reaction part times, Sean?
The derivative of x of t.
The derivative of x of t times x prime of t. Now, how many people are remembering this? Is it coming back? How many people think they have a better shot now at the second term? So go ahead, write down what you think now, learning from what you did there, what the second term might be. And what is it? What is it, guys? What do you think it is?
Partial derivative.
F with respect to
Y.
y evaluated at the inside.
X of t and y of t.
Now the chain reaction part times
Y prime of t.
y prime of t, times y prime of t. Is this rule going to help us take the derivative? Is this going to help us get the velocity along the space curve? Is this going to help us get the tangent vector? So you guys are going to help me out. Who's the x of t and who's the y of t? Who's the x of t and who's the y of t? Well, the x of t is
U
2 plus,
U1 t.
my y of t is,
3 plus U2 t.
okay. Now how many people think they could get x prime? What would x prime be? What would x prime be? What would x prime be? What would x prime be?
U1.
And what would y prime be?
U2.
Okay, so now let's just try to do it with this. We're looking at this derivative. So using this, it would be the partial derivative of f with respect to x. Partial derivative of f with respect to x. Now who's the x of t? Who's the x of t?
2 plus U1 t.
Then
3 plus U2 t.
times x prime. But you guys said x prime as you guys said x prime was
U1.
u1. Plus, now you guys fill in the second one. You fill in the second one. Okay, what do you have? What do you have? I helped you. I wrote the U1. I wrote the U2. What else do you have? What do you have?
Partial derivative
Of f with respect to
y.
y of
3 plus
u1t and then
3 plus U2 t.
3 plus u2t. Times u2. Okay, so now what I want you to do is I want you to be scribes and write all of that down all over again in that third component. Because that's the velocity term. I like the first two ones, Dr. Moore. I like the U1 and the U2. This other one's kind of a beast. Oh gosh. Okay, how many people are following? How many people are following so far? I mean, how many people are with me? I mean, are you with me? Okay, so what I want you guys to do is at Thanksgiving, I don't know how many people will actually show up at your house at Thanksgiving. I want you to show them this lecture. If they ask, what are you doing in college? I don't care about any of your other classes. My class is the only class that matters. Okay, my class is the only class. Don't all professors think the same way? My class is the only class that matters, okay? But just show them this lecture because they will be so impressed. They'll be so impressed. They'll be writing all this, you're like, oh, it's so hard, it's so hard. But guys, really, let's go back. What was the first thing I asked you to do? Draw an XYZ. What was the next thing I asked you to do? Draw a space sheet. What's the next thing I asked you to do?
Draw 2, 3.
Draw a 2, 3. What's the next thing I asked you to do?
Draw a unit vector U.
Draw a unit vector U. And then I said draw
Unit vector W.
the unit vector W. Then what did I ask you to do? Draw a line. And then we drew our corresponding line, our curve up on our space sheet. How many people if we take it a little baby step, if we walk a little baby step at a time, is it really impossible? Is it really impossible? But look at what's on the board. Just look at what's on that board. Is it pretty impressive you guys understand this stuff? Look at what's there and think about Calc 1 and think about where you're at right now. This represents a what, guys? That represents a what? That little x represents a what? A partial derivative. Impossible. No, you just treat y as a constant. Okay. Now, notice my tangent vector has its butt where? My tangent vector has its butt where? 2, 3, f of 2, 3. So I don't want the tangent vector here. This is all of the tangent vectors. This is all of the tangent vectors. I want the tangent vector at the point of interest, 2, 3, f of 2, 3. What value of t would we plug in here to get this tangent vector? Look at our domain curve. Look at our domain curve. Which value of t would actually point you at the point 2, 3, f of 2, 3? What value of t would you plug in here to get that? 0. So the tangent vector I want is the tangent vector at 0. So now you guys evaluate S1 prime at 0. You guys evaluate S1 prime at 0. Okay, so when you plug a 0 in, what do you get in the first component? What do you get in the first component of the, just U1, it's a constant. How about in the second component? U2. Now let's look at the third component. When I plug a 0 in, what do I get for the x coordinate there? And then I get a, 2. And then I get a 3. So it's not bad, just times U1, and then plus, we can finish this off, plus times U2. How many people followed that? Stand up again. You guys need to stand up. I don't know what to do. Okay, just turn to somebody in the room if you're here, and you guys just box me. Come on, box. Hunter. Rhett, come on up here and box him. Rhett. I won't breathe on you. Come on up and box. See, look at that. Don't you look impressive? It's like, okay, you really feel, guys, in a wide angle camera, you can feel pretty athletic. I'm not athletic, but I just feel like, okay, whoa. Doesn't that look, I just feel like, whoa, I'm Keanu Reeves. Whoa. The Matrix. What's the one he plays where he's some kind of assassin?
John Wick.
John Wick, yeah, sorry, John Wick, yeah. That's such a violent, those are so violent, I can't even watch them. They're just so violent, I can't even watch them. Okay, yeah, let's sit back down. I'm the kind of guy that, like, if I watch a horror movie, I'm not gonna sleep well. Anytime I see a horror movie, I can't even watch the commercials for the horror movie. I'm changing them so fast. You know, if you guys are a horror movie person, yeah, I just don't get you. Sorry. I mean, I know. Like, who are they making these movies, these slasher movies for? My friend took me to see the movie Halloween. Oh my gosh, that was the dumbest thing. It's Halloween. Let's go see the movie. The first Halloween. Okay, yeah, when you guys were negative whatever, 12, or something like that. Okay, now you're going to freaking hate me. Dr. Warren, that's done. Okay, we're gonna do the exact same thing all over again, but we're going to draw another line that runs not through you, but through W. We're going to have a line that runs through W, which would create another space curve. It would run through the point 2, 3, F of 2, 3. It would create another space curve. Instead of calling it S1, I would call it S2. And guess what? When the smoke cleared and you evaluated S2 prime at 0, can you take a guess at what the final result would be? If you're willing to do that, we're not going to do it all over again. If you're willing to do that, if everybody in here can write down what the tangent vector in the W direction would be, the tangent vector coming off my curve up there on my space sheet corresponding to the line underneath heading in the direction W, can you write down what you think that tangent vector would be? Okay, does anybody, if you screw it up, guys, we're redoing everything. We're going to take a half hour and redo the whole thing again. So what do you think the first component would be?
W1.
W1. What do you think the second component would be?
W2.
What do you think the third component would be? Oh gosh, here we go.
Partial derivative.
With respect to S, or 2, 3.
At 2, 3 times
W1 plus partial derivative.
2, 3.
times
W2.
times W2. Guess what we had to do in the first class? Redo it all over again. Okay, you're like, oh, thank goodness. Now, guys, let's give these vectors names other than S1 prime and S2 prime at 0. For lack of anything better, I'm going to call it TU. And that stands for the tangent vector in the U direction. The tangent vector in the U direction. And guess what I'm going to label this one? Guess what I'm going to label that one? TW. So it's going to be TW in the tangent vector in the W direction. Now in your drawing, in your graph, in your space sheet, mark TU and TW. In your drawing, back in your drawing, mark TU and TW. And I'll do the same thing on mine. So this is my TU and this is my TW. How many people are following? Okay, if you didn't hate me up till this point, okay, if I've somehow managed for you not to hate me, you're gonna hate me now. Guys, what we need to do is find the plane. We've got to find the plane that holds these two tangent vectors. We've got to find the plane that holds those two tangent vectors. I want the plane that contains this vector and this vector. I want the plane that contains my TU vector and my TW vector. When I say plane, you say, I hate you, Dr. Warren. When I say plane, you say what?
And
X minus n equals 0.
It's a scalar equation because we have a dot product. Okay, you probably have already forgotten, but this vector x, because it was an arbitrary point on the plane, what did I just say?
It's an arbitrary point.
It was just the vector x, y, z. It was just an arbitrary point in three-dimensional space. Now what's A's job? What's A's job in this equation? What's A's job? Positions that plane. And what's N's job? It's a normal. It points out of the plane. It points perpendicular to the plane. Okay, let's try to think about A. Can anybody think of a position vector that would start here and point up to this plane? That's, somebody said, what? Can anybody think of a position vector that would point up to this plane, position this plane?
2, 3, F of 2,
2, 3, F of 2, 3. I agree with that. So let's put that in. Let's put that in there. Now you're like, please don't, Dr. Warren, Dr. Warren. Now we need what? Now we need what? Now we need what? Now we need N. Now we need N. Look at somebody and say, now we need N. So you guys just look at me.
Now we need that.
Now we need N. Okay, so guys, I'm gonna draw my N. My N sits perpendicular to the plane that contains TW and TU. How could you possibly find a vector that sits perpendicular to both TW and TU? Take the cross product. Now the way I've drawn it here, is it TU cross TW? It doesn't matter. Is it TU cross TW or is it TW cross TU?
TW cross TU.
TW cross TU. So that's what we're going to do, and you're going to hate me. Okay, we're going to write down our determinant. This stupid determinant. It'd be I, J, and you're like, Dr. Warren, why are they so close together? Just wait. Okay. So what would go in this row? What would go in this row?
TW.
The components of TW, put them in there, put them in there. Now guys, let me make your life easier. Let's make all of our lives easier. Are you willing to accept, if we just ignore the 2, 3, that the 2, 3's there, are you willing to do that notationally? Trust me. Let's just use fx. Let's just use the symbol fx to represent fx of 2, 3. And similarly, let's just let fy, because it'll just make this determinant, taking this determinant so much easier. No. I don't know if you guys saw that or not. I don't know if you guys can read it at home. It was awfully blurry when I was looking at your guys' stuff. This first component is W1. The next component is, and the third component was.
Fx W1 plus Fy W2.
Okay, now fill in the second one. Fill in the one for TU. Fill in the one for TU on that third. And now guess what you guys get to do. Now guess what you guys get to do. Now guess what you guys get to do. You get to take the determinant. You get to take the determinant. And you better have a long, fresh line. You better have a long, fresh line. I'll put my vector there, and I'm gonna stop my vector over here. I'm gonna stop my vector over here. So you take the determinant instead of Dr. Warren. Now, Dr. Warren's gonna wash his hands. This is when it's good for me to see. How many people feel like they got the last component right? How many people feel like they got the z component right? I mean, like, if you're not certain about any of it, you're kind of like, well, I'm kind of certain about the last one. Notice I left a little tiny space over here. I left a little tiny space over here. What did you get for the last component, guys? What did you get for the last component?
W1, U2
W1, U2
plus W2, U1,
minus
W2, U1.
W2, U1. Did anybody else get that? Did anybody else get that? Did anybody else get that? Okay, let's start with the first component. Let's start with the first component. I cover up this column, and I would do W2 times that minus U2 times that. So that's what we're going to put in there. W2 times that. You're like, oh, thank goodness we're not writing down the 2 3s. Fx U1 plus Fy U2 minus U2 times Fx W1 plus Fy W2. Did anybody get that? Did anybody get that? Did anybody get that? Did anybody get that? Okay, now guys, you're gonna hate me, but I'm not gonna finish that one. I'm not gonna finish this one yet. I'm not gonna finish this one yet. What I wanna do here is I just wanna do a little bit of math in this first component. I wanna do a little bit of math. The W2, let's distribute. Let's distribute. Now before you guys write anything down, I'm gonna save you some effort. Notice, if I look here, I'll get a W2 times Fx U1. But to the second one, I'm going to get a W2 times U2. Now look over here. When you distribute this minus U2, you're going to get, just look at the Y. Just look at the Y. I would have a minus U2 times Fy W2. Minus U2 Fy W2. But here you're going to get a W2 Fy U2. What happens with those two terms? What happens with those two terms?
They cancel out.
They cancel out. They cancel out. So the y terms cancel out. The y terms cancel out. So write down. When you distribute and clean up a little bit, write down what that first component simplifies into being. So what do you guys have? What do you have for me? What do you have for me? What do you have for me? What do you have for me?
W2,
W2,
FX, U1,
fx, u1,
minus
minus
U2,
u2,
FX, W1.
w1. Did anybody else get that? Did you guys get that at home? Did anybody else get that at home? And you're like, Dr. Warren, you're done, right? No, I'm not done. Okay. Let's do a little bit more algebra. Let's do it. What's alike in both one of these? What's alike in both of those? What's alike in both of those?
FX.
fx. So let's pull that out. Let's pull the fx out. Now I'm going to write down this last component, W1, U2, minus W2, U1, in both of these locations. Now, I'm not doing it, you guys are doing the other component. I want you to simplify it. I want you to take whatever you got in that line, and I want you to simplify it down like what we've got there. This is where the 6 feet barrier is just killing me. So I'm moving quickly through. Who canceled out in the second one? Who canceled out with the second one? The fx. How many people had fx cancel? How many people had fx cancel? Okay, so I've got my minus from this being the middle term. I've got my minus from that being the middle term. And so the fx's cancel, and so I'm left with minus W1 Fy U2, and then I got the minus U1 Fy W2. Now you guys help me not make a mistake. Did anybody else get that? And then I've got the minus going around like that. Then what can I factor out of? That term? F1, Fy, minus Fy, times W1 U2 minus U1 W2. Did anybody else get that? You're like, that's one, what the hell are we doing? If I forget, what are we doing? Guys, what are we doing? What are we doing now? What have we been doing? What are we trying to do here? What is it we're doing again?
Trying to find the plane that contains both of those vectors.
We're trying to find the plane that contains the tangent vector TU and the tangent vector TW. From two arbitrary paths heading away from two lines. And we're walking along our curve up here. Now, the cross product represents the what in the plane? The normal vector. Okay, now, look here. We've got, let's look at this last one. We have a W1, U2 minus a W2, U1. Now look at the second component. Let's look at this scalar here. Here we've got a W1, U2 minus a U1, W2. Are these the same thing? Are these the same thing? Is this, let's just call it pumpkin. If this was pumpkin, if this is pumpkin, thank you. If this is pumpkin, would this also be pumpkin? Would that also be pumpkin? Would that also be a pumpkin? You're like, Dr. Warren, I'm not sure. W1U2, W1U2, minus U1W2, flip U1W2. Is this not the same as that? Well, like Dr. Warren, your other one's screwed up. This is W2U1 minus U2W1. It's jacked. This is a W1U2, and this is a W2U1. You're like, wait. This guy's the same as that guy. True or false? True or false? And this guy's the same as that guy. True or false? True or false? The only difference between pumpkin is this isn't pumpkin, but it's negative pumpkin. It's negative pumpkin. So if I would factor a minus out here, these guys would switch, and I would get my W1, U2 minus U1, W2. How many people are following? How many people are following so far? Now what can I do with that scalar? Look guys, is the scalar not in every single term? Is that pumpkin not in every single term? Is that pumpkin not in every single term? So what could you do with that pumpkin? What could you do with that pumpkin? Pull it out, pull it out. So pull the pumpkin out in front of the vector. Factor that pumpkin out in front of the vector. Now guys, this is active learning versus passive learning. If you're teaching, this is active learning versus passive learning. It's much better to keep your students doing it than them just copying, because they're having to react with their own brain. So my normal vector could start with a scalar. My normal vector could start with a scalar, and what would the scalar be?
W1, U2.
W1, U2
Minus U1, W2.
minus U1, W2. Then what's the vector part? What's the vector part? Negative fx, and then negative fy, and then 1. Did anybody get that? Did anybody get that? Did anybody get that? Now, oh gosh. Voila! This is vodka. This is not really water, sorry. This is vodka. So, it's not really vodka. I wish it was vodka. You're like, Dr. Warner, we wish we had vodka. Okay. Robert, I think you do have vodka, don't you, Robert? It's hiding there, isn't it? No, you're a little too alert. Emily, there's the vodka, yeah, okay. Raylan, no vodka, right? Get you a little bit, okay. All right, okay. How many people have followed? I mean, it's been a long adventure, but how many people have followed on our Japanese Death March? I mean, how many of you? Okay, now let's see if you remember. I'm afraid. What does FX really stand for? Do you remember? What does FX really stand for? It was an abbreviation for what? Partial derivative at 2, 3. So put it back in. Put the 2 3s back in. put the 2 3s back in. I'm like, Dr. Moore, thanks for doing that for us, because that made it a lot easier. So we didn't have to write all those. How did you know to do that? Oh, I just did it at home at breakfast. I was like, I'm not doing that. Okay, now this is a
Vector.
vector. This is a,
Scalar.
this is a,
Vector.
this is a,
Scalar.
this is a,
Scalar.
this is a.
Vector.
Now what does a scalar do to a vector? What does a scalar do to a vector? It's all in the name. What does a scalar do to a vector?
Scales it.
It scales it. Like for example, I'm running back, we haven't used props. But I could have a vector, I could have a vector and I could scale it and it would become a different vector, but it points in the same direction. I could multiply times a negative and it would flip it around, but it would still point on the same line. Now n represents what again? What does n represent what again as far as this whole game?
Normal vector.
The normal vector. Guys, does it matter that the normal vector points up or down from the plane? Would it matter? Would it still be a legit normal vector if it pointed up or down from the plane? As far as being a normal vector, does it matter how long it is? If I stretched it out to here, would that still be a legitimate normal vector? And if I shrank it down to there, would it still be a legitimate normal vector? So if I just completely ignore the scalar, if I just completely ignore the scalar that I just pulled out, would this still be a legitimate normal vector for my plane? And you're like, what do you guys say? Would it still point perpendicular to the plane? Now you guys should say, holy hell, Dr. Warren, that's remarkable. So say that.
Holy hell, Dr.
Oh, that's remarkable.
Okay, I need it louder than that. I know we're gonna get COVID. Say it again, from the grid.
Holy hell, Dr. Warren, that's remarkable.
Okay. You're like, no, it's not Dr. Warren, it's not remarkable at all. No, guys, this is so remarkable. Like Dr. Warren, I'm not getting it. Guys, were U and W in any direction we wanted down here? They were just normal vectors pointing in any direction we wanted. But notice this thing that's directing the plane, my normal vector, doesn't position the plane, but how I move it, do you see, if I move my normal vector, it's describing how the plane sits in three-dimensional space. If I've got a plane, and I've got a normal, it's like you guys see great, but then I'm looking at the great. Look at behind you. You're like, oh, this doesn't look like. Do you see how my normal vector really describes how this thing's oriented in three-dimensional space? The orientation of the plane doesn't depend on W1, W2, or U1 or U2. One more time, Dr. Warren. The orientation of this plane doesn't depend on the directions we're moving away from 2, 3. This holds all of the velocity vectors moving in any direction on a line away from the point 2, 3. If you move in any other direction, your tangent vector is going to lie in this plane. And guess what we call this plane? If you just had to guess what we call this plane? The tangent plane. So say that.
The tangent plane.
Say that. The tangent plane. The tangent plane. Do you think the equation of a plane that holds all of the velocity vectors is important? Do you think the equation of a plane that holds all the velocity vectors would be important? Just like the tangent line back in Math 235, Dr. One just shut up. Just like the tangent line back in Math 235, if I pick a point and I draw the tangent line, this is the line that best approximates my curve near that point. Does that make sense? This is the line, if you said, use a linear approximation, and guys, all you're learning in engineering all through this entire thing is linear stuff. I'm just letting you know. You're learning no nonlinear stuff in your whole engineering program, okay? It's a linear approximation. If I jump up a dimension and I say, what's the best plane? What's the best plane that represents the surface that I'm at? It would be at the point, would be the tangent plane. So we're almost done. We left off here. Dr. One, I'm sound asleep. Dr. One, I'm sound. So why don't you stand up? Look, okay, Caitlin, come on up to the grid. Talk to them. Tell them wake up. It's much easier. There's accountability in the classroom. There's not accountability.
Wake up.
Michael, I don't know if Michael has a lot of accountability there. Michael, you remind me a lot of me, I think. It takes a lot to focus, doesn't it?
It's a lot.
It takes a lot. Okay, Sean, you're pretty good at focusing. I mean, Rhett, you're really good at focusing. Caitlin, awesome. David, you're with me. It's good. You're there most of the time. Stuart, you're great. Sit back down. Cosmo, you are awesome. You are awesome focuser. Cameron, you're like me, man. Roberto, you're in between. Hunter, you're pretty good. Robert, depends if you got vodka. And then you're not so good. Ava, I'm thinking you're good, but I'm not sure. Lizzie, I know, I've seen you here, so. Luke, definitely good. Okay, who's had COVID? Raise your hand. Who's had COVID this semester? Raise your hand. Does anybody? Nick, Luke, sorry, I know I see your hand, Luke. Okay, so not bad. Oh yeah, that's right, David, okay. Somebody asked me and I said, I think about 10% of my students have had COVID. I think about it, so I have 35 and I've seen 3 hands. So I've seen 3 hands, including Luke's. Okay, but I think it may be more. Somebody was asking me, is it more than the national average? And I'm like, I'm pretty sure it's more than, 1 in 45 is the national average, and I think we're doing a little better, or a little worse, I guess. It depends how you define a positive, I guess. I'm sorry. Okay. A is the, I hate you. A is the position vector, N is the normal vector. Does it make sense why 2, 3, f of 2, 3 is the position vector for positioning the plane? Okay, what is the simplest normal vector? Well, we said, just ignore the scalar. Negative f of x of 2, 3, negative f of y of 2, 3, and then the happiest thing is it's just a 1. So let's put that over here in our equation, because that's going to help us land this aircraft carrier. Land this aircraft on this carrier. Okay. In this next line, let's just do the vector subtraction. Let's just get the vector subtraction done. If I have this vector minus this vector, and I want my vector form of it, I would have what as my 3 real numbers? I would have what as my 3 real numbers there? I would have doing the vector subtraction, I would have a x minus 2, a y minus 3, and then a
z minus f of 2, 3.
Okay, let me look around the room. Who had me for Math 235? Who had me for Math 235? Okay, Emily, Nick, Cameron, Stuart. I made you guys memorize a flashcard, and I want to see if any of you guys remember it. Okay, this is a test. If I ask for the equation of the tangent line to the point CF of C, we've got a function y equals f of x. Does anybody at all remember the flashcard for the equation of the tangent line at the point CF of C? I'll help you. It's a line, so it'll have a y. Y minus, okay, I'll help you. F of C, the y coordinate, it's a point slope form. Who's the slope? Who's the slope? You should remember this. Come on, who's the slope?
F prime C.
F prime of C times, it's the point slope formula line, times
X minus C.
x minus c. This was the point slope formula. This was the point slope formula for a tangent line. Okay, now you guys are gonna do the dot product for me. You guys are gonna do the dot product. We're here, we've got this vector dotted with that vector. Now listen to me, before you start, when you're all said and done, the only thing I want left on this side, here's the 0, the only thing I want left on this side is your z minus f of 2, 3. The only thing I want left on that side, you guys take the dot product and take everything to the other side. Active learning. You guys get z minus f of 2, 3 all by itself. For sake of time, let's just see if anybody has it. How many people have the z minus f of 2, 3? How many people see where that came from? Just the one dotted with that. What do you have over here on the other side? What do you have once you take it across to the 0? What do you have? Partial derivative of f with respect to x at
2,
2,
3.
3.
Times
X minus
X minus 2.
plus.
at 2, 3 times
Y minus 3.
y minus 3. Now it's only taken an hour and 15 minutes. But guys, does this look remarkably similar? If you squint, does this look remarkably similar to our equation of our tangent line? If you're looking, it's not y equals f of x, but it's z equals f of xy. And we have the partial derivative. Remember, it's two-dimensional. Ooh, does anybody remember this? Slapshot. What's the word we gave for the derivative in higher dimensions? We don't call it the derivative, the d vector. What do we call that? The gradient, yeah. So it's the partial derivative, the first component. It's the first component of my derivative vector, my gradient vector, evaluated at 2, 3 times x minus 2. The same thing that we have here. Almost like our x minus c. But our c now is a vector. And then we have the partial derivative of f with respect to y evaluated at 2, 3. But now times y minus the second component, y minus 3. And it even gets better. If we use gradient notation. We can rewrite this like this. If I let c be a vector 2, 3, then this is loads of fun. It's z minus f of c equals something dot x minus c equals something dot x minus c. So this is almost looking exactly like my tangent line, except I have a dot product x minus c. Now they're vectors, And what would be the vector that you would dot there, on there? It would be, first component would be this. The second component would be that, which is your
Gradient.
gradient vector. So it'd be the gradient of f at c. So if you can remember this, you can remember your equation here. And this almost looks identical to the tangent line. Our tangent line's important. Our tangent line's important. Okay, are tangent planes just equally as? Do you think tangent planes are just equally as important? So guys, when they talk about, anybody in engineering here? Anybody, have you guys taken any engineering classes yet? Have you taken statics or dynamics or anything like? All that theory is based off of linear theory. Okay, they just don't tell you that. So this is, it all goes back to linear theory. Even though my surface is highly nonlinear, even though, like, look at my arm. How many people recognize my arm's not a plane? Well, I guess to you guys it does look like a plane. Okay, so I'm two-dimensional. But how many people recognize my arm's not a plane? But if I keep zeroing in, getting closer and closer, do you see how ugly my hair is? Okay, but no, but do you see, guys, how like a plane can be a reasonable approximation near the mole? Can you see near the mole there that the plane could be a reasonable approximation? And that plane we would call the mole plane. No, we would call it the tangent plane. The tangent plane. How many people, close your eyes, you can leave with this. Okay. What's the equation of the tangent plane? Tangent to the point 2, 3, f of 2, 3. What's the equation of the tangent plane? Z minus f of 2, 3 equals partial derivative of f with respect to at 2, 3 times x minus 2. Are you done?
No.
Plus
Partial derivative of respect to y
times
y minus 3.
y minus 3. And if somebody asks, where does the plus come from? How's there possibly a plus in this? You tell them it's coming from the dot product. Okay, did you guys learn anything today? Did you learn anything today? It was a long adventure. It was a long adventure. Thanks for coming. Thanks for coming and put up with me. Are you guys able to at least see enough in the grid, guys, to get notes? Are you able to see at least enough? Okay, I'll record the video. I'll put up the video too. It's gonna get cold. It's gonna get cold. Oh, thank you guys. Thanks, Sean.
Class.
Oh, thanks, Red.
Thanks, have a good day.
Mom and Dad still good?
Yes.
Okay,
All
okay.
goods for Thanksgiving.
Okay, that's what I want to do.
Good stuff today, good stuff.
It is, Michael, it's really beautiful stuff. It's
Yeah.
the fact that, like, it doesn't matter which direction you go, you can still lie up in the same plane. That's just
More to come, right?
more to come, more fun to
And I'll
come.
see you in the office hours. I'll come for the quest.
Yes, yes,
Oh,
that's
awesome.
perfect. All right, perfect.
I'll see you later.
Oh, all right. Stop this.